PhD nearby Stony Brook, or nearby.
Yeah, relatively.
I'm actually in experimental particle physics at Atlas, and then she did her PhD in postdoc in mines before going more towards astrophysics in Santa Cruz. Now she is a senior researcher at Goddard Space Center in Washington, D.C. So she's going to tell us about some cool gamma-ray physics and cosmic explosions. So let's take it away.
If you have pretty slides, we can turn off the lights.
Oh yeah, we can dim it.
I mean, it wouldn't be an astrophysics talk if there weren't some pretty slides, right? So, yeah. And so thank you, David, for the nice introduction. I also like to start a little bit, just a little bit about who am I to kind of folks can kind of see my path, because I feel like it was certainly nonlinear. So I grew up in Colorado, got my PhD in engineering physics, or got my bachelor's in engineering physics, and did an internship at Fermi Lab back in the day. And that was really when I fell in love with particle physics. So after that, I went to Stony Brook to get my PhD in particle physics. I worked on Atlas. And this was right around the time when it was turning on. I was a postdoc when the Higgs was discovered, to date myself. So it was like a very, very exciting time to be in particle physics. I did lots of new physics searches and detector operations. I did a postdoc at the University of Mainz in Germany. And then, I had been working on Atlas for a while. I decided, you know what, I want to try something different. And so I went to particle astrophysics, because if particles on Earth are interesting, particles in space are even cooler at some level. And so I became a part of the Fermi Large Area Telescope, the LAT collaboration. And my gateway drug was dark matter searches, and then I got more and more and more into astrophysics and particle acceleration. I am now an astrophysicist at Goddard Space Flight Center, and have been working more on, to continue the theme of particle acceleration, multi-messenger astrophysics. I was the analysis coordinator for the LAT team. I'm now the Swift Observatory project scientist. And I'm also really at heart an instrumentation person, and so a lot of my research is on developing a next generation gamma ray telescope.
LAT is Fermi.
LAT is Fermi, yes. So it's one of the two instruments on Fermi. And we'll go into all of that in more detail. And so if folks have questions, feel free to shout them out, and we'll hopefully make this a little bit more of a dialogue than me just talking at you. So this will look familiar, I think, to lots of you folks to start with a pretty picture of the Milky Way. And of course, so this is our galaxy, and what you're looking at is an optical light. So, if you had really good eyesight and good resolution and were in a really dark place and could see the full sky, this is what you would see with your eyes. And we know that optical light tells us part of the story. But if we really want to understand all of the physics and the science that's going on in star-forming regions, in clouds of dust and gas, and where things are happening throughout the galaxy, we really need to look at more than just optical light, because that doesn't tell us the whole story. If we want to know where particles accelerating, particles are getting absorbed, if we want to understand where things are happening, you want to really span the full electromagnetic spectrum, going from radio, which is shown at the top, all the way to the highest energy form of light, gamma rays at the bottom. Because each of these different wavelengths tells you a little something different about the source that you're looking at. And so, the electromagnetic spectrum covers, 19 orders of magnitude, or even more really than that, because it's not bounded. And so to cover all of this, you need lots and lots of different mechanisms for detecting all of this light. And so, we start at the top. What does it get through the Earth's atmosphere? And I think, fortunately for us, as I said at lunch, for human beings, gamma rays don't make it all the way down to Earth. But as a gamma ray astronomer, it means that you really need to go to space if you want to observe the higher energy forms of light. And so the more kind of, visible infrared, ultraviolet, this is produced all through normal stellar processes. Thermal emission, the expansion of the universe causing my bird background. This is where this kind of light occurs. But if you're looking at the highest energies, that's where you need some extreme things happening. So you need explosions, you need some extreme fields, you need particle acceleration, you need magnetic fields, things like this, charge particle interactions. And that's where you get the gamma ray sky, is through these really extreme events that are happening in the universe. And of course, the quiescent sun does emit gamma rays, but it's really at the lower end of the spectrum where we really see the sun flare up is when some sort of, big coronal mass ejection happens and particles get, bent around in magnetic fields, and then you see gamma rays. And so that's when the exciting stuff happens. So kind of like, the parallel of the blind people trying to understand what an elephant looks like. In our world, the elephant is the universe, and we're just trying to figure out all of the different pieces of it. And so enough about just light. I know I'm in a particle physics heavy group. What about all the other things that get produced in the universe? I mentioned charged particles, we all know neutrinos, and then, most recently gravitational waves. Like, there's lots of ways that we can try to observe the universe beyond just the electromagnetic spectrum. And so all of these ideas were kind of culminating about 100 years ago about, understanding gravity, understanding gamma rays, understanding, what the heck neutrinos are, and radioactivity and all of these different aspects of, Earth. But fast forward, about 100 years, and we actually are having telescopes and observatories that can start to measure gravitational wave interactions via the LIGO detectors, which was a 40-year investment by the National Science Foundation before they actually got, detections and signals. Gamma rays in the mid-2000s, we had two very important telescopes that were launched to observe this highest energy form of light. And then, of course, we have the neutrino observatories. Amanda preceded IceCube, and these are really what has opened up the floodgates to understanding the universe in a completely different way. And what we see is that gamma rays, because gamma rays are measuring the most extreme events in the universe, they're the connection between the electromagnetic spectrum and gravitational waves and the electromagnetic spectrum and neutrinos. And so that's, a little taste of why gamma rays are very important for understanding the multi-messenger universe. And so I'll talk a little bit in more detail about these particular observatories. First is the Neil Gehrels Swift Observatory. It was launched more than 21 years ago in 2004. It is made up of 3 telescopes. The High Energy Wide Field Monitor is the BAT, the Burst Alert Telescope. It was designed to observe gamma ray bursts, which are a really intense, brightest thing in the universe when it happens. And of course, gamma ray bursts emit in gamma rays, and so it's a gamma ray telescope. And then it will slew very quickly within seconds once an onboard detection happens to follow up with both the X-ray telescope, the XRT, and UV optical telescope. And so it can detect and characterize gamma ray bursts within seconds, and it's an incredibly unique facility in the fleet. Now, it has been in low Earth orbit for 21 years, and as I was also mentioning at lunch, its orbit is decaying, and so we've been investing in the potential of boosting the orbit, which is a whole cool, interesting thing of how this is working, and I'd be happy to talk about it later if folks are interested. And so this is a somewhat dated sounding animation, but what was really cool about gamma ray bursts is that we found that they're isotropic, so they're extragalactic, they're coming from everywhere, they're incredibly bright, and Swift observes about 90 of them and characterizes them a year. And so the second observatory is the Fermi Gamma-ray Space Telescope. It has 2 instruments on it, the Large Area Telescope, which is the box on top of the spacecraft, and then the Gamma Ray Burst Monitor, which are scintillating detectors that are all around the base of the spacecraft. And so what the Gamma Ray Burst Monitor does is give you an observations of the full unocculted sky in the energy range from like the hard X-ray to the gamma ray. And then the Large Area Telescope sees about 20% of the sky at once. It orbits in 90 minutes. Every 2 orbits, it will observe the full sky, and it observes from about 20 MeV to over 300 GeV, really all the way up to a TeV, but it was designed for that range. It was launched in 2008, so it celebrated its 16th launch anniversary, and has been doing some really awesome science ever since then. So this is a picture of the Fermi LAT gamma ray sky. The bright band in the middle is the Milky Way. It turns out there's lots of particle acceleration and interactions in the Milky Way, unsurprisingly. And so, but there's lots and lots and lots of things in this picture. We could start from the farthest away, the extragalactic sources. There's active galaxies, the cores of active galaxies that are actively accelerating particles. There's globular clusters, there's starburst galaxies. A little bit closer in the galaxy, we have pulsars, which are just rapidly rotating neutron stars. We have pulsar wind nebulae, lots and lots of supernova remnants, things like that in the galaxy. Locally, as I mentioned, the sun makes gamma rays. Also, lightning makes gamma rays that we can detect on board, which is interesting. They're called terrestrial gamma ray flashes. And there's over 5,000 sources in the LAT catalog. And that's about as many as you can see with your naked eye, optical sources. And so, like, there's really a rich amount of science across many different types of sources that we see.
Sorry,
in
is it true that today each gamma ray burst is simultaneously detected by Swift and by Fermi?
No. Only because they're both in low Earth orbit, sometimes their orbits are not in the same location. And so if Swift is on one side of the Earth and Fermi is on the other side of the Earth is occulting, so they won't be detected by both. Swift also has a smaller field of view, so the GBM sees the most gamma rays of any observatory, but it doesn't localize them very well. It localizes it to 10 degrees, so following up is really hard.
But many of them are seen simultaneously.
Yes, absolutely. Many are. So it's not required that they are. They don't have to be. But Swift also has a bit smaller of a field of view. It observes about a 12th of the sky. And so there are many that are simultaneous. And also, Swift can follow up Fermi sources. So if the bat doesn't see it and it's coming around in the orbit, Swift can follow up to observe the GRB that happened. So they work together. And in fact, I think it was a few days ago, there was a LAT detected GRB on board. And this is really unique because LAT is a higher energy telescope. And the fact that the LAT detected a burst is quite rare. It has observed about 100 in its lifetime, but it was sufficiently bright that it triggered the LAT. And so then Swift actually is not currently taking data right now with the XRT and UV telescopes because we're working on this reboost mission. But that would have been a very good candidate for follow-up with the XRT and UV.
Can you remind what the angular resolution
Of Fermi?
Yes.
So it can go down to about 1/10 of a degree, so arc minutes. Swift is arc minute, sub-arc minute. GBM is like tens of degrees. And of course, this picture is there's no transient astrophysical sources that are buried in here. So like GRBs aren't represented in this. But the GBM sees about, one a day on order. And so now so speaking of gamma ray bursts, in 2017, there was this really amazing event that happened. And what you're seeing right now is a representation of two neutron stars that were orbiting each other, and their orbit decayed, and the two neutron stars merged. And this merging neutron star was detected by the LIGO detectors, and there were upper limits placed on by Virgo. And so they saw this gravitational wave strain, and that gravitational radiation stopped, so that spike at the plot of the frequency map is occurring at the time of these neutron stars merging. And at the time when they merge, this is when a short gamma ray burst is launched. And so this launch happens, and a short gamma ray burst, so short means less than 2 seconds, long is the total duration of the peak of the flux. A jet is basically ignited on the polar axes of the merger. And if that jet is pointed in our direction, we will actually see a spike of gamma rays from an instrument like the Swift BAT or like the Fermi GBM. And so this is exactly what happened in August 2017. Was LIGO detected this merging neutron star event in its gravitational wave strain map, and the Fermi GBM detected a relatively typical short gamma ray burst a few seconds after LIGO detected the merging neutron stars. And so here is what in somewhat real time it would have looked like. And so, what happened in that 2 seconds is a whole lot of really, really interesting, very extreme physics, because you have basically the two merging neutron stars, which are stars as dense as the sun and about the size of Manhattan that smash together, and then all of these processes are happening, and then this really intense burst jets are launched, and so really it's a lot of really cool stuff that's happening. And so then what happened is all of the telescopes, and by all I mean all the telescopes, started observing this event. And what they found is that this was consistent with a kilonova emission. And so what happens in a kilonova is this is where rapid process nucleosynthesis happens, and there's this isotropic emission in all directions and across the electromagnetic spectrum that tells the details about the merger, the ejective velocity, the mass of things, the composition of things, and all of this is through multiple different wavelengths and observations. And I mean, we're still following it up because the ejected material is still expanding into the nearby medium, and we're seeing interactions of things happening.
Sorry for my ignorance.
Yeah, sure.
Like all those things, are you saying they were, can you go one slide back?
Yeah, sure.
Are you saying all of them were detected? All this optical stuff, like we know it was a kilonova? Because I know they have seen GRB and radio or something.
Yeah.
But
So
they
it
have
was,
also seen all that stuff?
it was observed by Chandra.
Like that thing?
Yeah. Well, I mean, so we weren't. This is just a representation because we don't have the resolution to actually see the kilonova. It was far enough away.
Oh, so we did not see a
Well, we saw
What did we
what is
see?
consistent. So we saw what is consistent with kilonova emission based on kilonova modeling.
But wasn't it just gamma rays plus radio?
No, we saw it in X-rays. We saw it in UV. Swift saw it in UV.
So UV
we
was-
saw it in optical. We saw it in infrared. Like we saw it across the electromagnetic spectrum. It was observed. Hubble saw it. Everything.
And part of it is not thought to be a jet, part of it is thought to be a genuine kilonova?
Yeah, absolutely. Because the jet is relatively short-lived.
Okay.
But you mentioned that the jet was pointing in our direction. I think that the analysis will now made it absolutely clear.
It was
that
off.
the jet was pointing exactly 18 degrees away from us.
That's correct.
And what we saw was not a regular gamma ray burst, but what we saw was emission from cocoon breakout, which is a completely different story. And this gamma ray burst is actually very different from all other short gamma ray bursts that have been seen. It was extremely soft. It was smooth. It was not varying. You have shown the light curve. The light curve just goes up and down, where other gamma ray bursts goes up and down like crazy. And it was weaker by 5 orders of magnitude than
Well,
other
Is it
We
not
have-
consistent with just looking off angle? Because it was
No,
so,
it's not.
it didn't
No,
trigger
it
the,
is not. This is a very common mistake. It is not Doppler boosting. It was a different
I
phenomenon.
didn't mean Doppler booster, but just a different piece of the emission. I mean,
It was different piece of the emission in the sense it was not coming from the jet.
yeah,
Because
the
we're
perimeter.
off-axis,
Well,
I'm just saying that there's,
Because we're off-axis viewing it, or?
Because of the off-axis viewing, we did not see the original jet of the GRB.
fine.
Some other civilization, which was in some other galaxy, saw a regular GRB.
Excellent, you answered what I was trying to say. Namely, I thought you were trying to suggest this couldn't be that phenomenon because we looked at it from a different side. It's perfectly consistent with
It
a
is-
single, simple model, right?
It is, the bottom line is perfectly consistent with 2 neutron star merging and a gamma ray burst. But what we saw was not
It's
a regular
quite
gamma
different.
ray burst.
Well,
Yeah.
What
yeah,
we saw
just-
is a shock breakout out of a cocoon which was forming around this GRB. This is a different story,
well,
a
okay.
different
It's a
physical
physical
process.
thing, but
Yes.
we're seeing a different aspect of it. Good.
yeah, and I think the thing I would add to that is we just don't have sufficient data on other short GRBs. right? So we don't know what we were looking at on all the other GRBs. Some of them are very complex. Every GRB is a little bit different. I mean, the spectra are. So I think that like if we had all of the observations, if we had all of the gravitational wave data, if we had all of the UV, optical, infrared, X-ray observations of all of the short GRBs, we would know more about the pictures.
Sometimes people refer to short GRBs as SH GRBs, which means short hard GRBs, because they typically have much harder spectrum.
Yeah.
There is not known any other short GRB with such a soft spectrum.
There's a few that are very similar.
I
Anyway,
disagree with
anyway.
this statement.
Okay.
But I mean, it doesn't take away from the picture, if I
It
think we're in
doesn't-
agreement, that this
Yeah.
was a binary neutron star merger
No,
viewed
no,
from a different
absolutely.
angle
It
than
was-
all the short
It would
term.
be nice
more
to
than
discuss
that.
this after the
But-
talk, I
but-
think. No, seriously,
Yeah.
it sounds very interesting. Okay.
Yeah, no, and I mean, I think that what this did was, I mean, we learned a lot about a lot of things with just one event. And it's because we had a lot more information than what we had before. And I think this is the point that I'm trying to make. It's when you have new data, new information, you learn a lot more about models, about the physical processes that are happening. And so what are some of the other things that we learned about this? In addition to a lot of very interesting GRB physics, we learned elemental origins. So a lot of where the heavier elements came from was an outstanding question. And we know that a lot of it comes from merging neutron stars. In particular, things like, platinum and gold. These are things that, like my mom cares about when I tell her what I work on. It's like, we learn about where all the gold comes from. And she's like, that sounds cool. We're able to put new constraints on things like the Hubble constant by, measuring it in a completely different way, by measuring the speed of light versus the speed of gravity. So this is a very interesting new kind of measure that we can, start to put other handles on. The other thing that I think is really cool is doing a measurement of, modified gravity to explain dark matter, because gravity and light interact with the universe in a similar way, and so that rules out a lot of modified gravity theories of explaining what we see as dark matter. And so this gives us another handle on understanding the fuller picture of the universe. And so we've been talking a lot about gravitational waves. I also want to get back to some particles, because this is also a long-standing, 100-year-old question about where particles are accelerated. We see really, really high energy particles, in particular protons, coming at us. And where are these coming from? And for context, these are, 5 to 7 orders of magnitude higher energy than anything we could create on Earth. We know that some of them are likely galactic. We know that some of them have to be coming from outside of the galaxy. This is like a pretty, well-known, like the flux plotted as a function of energy. And so the challenge with the charged particles is that they don't point back to the source like gamma rays do. And so if we're trying to say, like, what was the source of that really high energy proton, we know it was bent all over the galaxy in any intergalactic magnetic fields, and those are really hard to map. And so we need to figure out another way of measuring them, because it's hard to see where they come from directly. Now, protons interact via photons on this little chalkboard thing that's up here, and they can create neutral pions. And those neutral pions can decay into gamma rays. And so, we already have a little bit of a handle on how we can detect gamma rays. And so that's one way that we could try to see where proton acceleration and proton interactions are happening. The challenge is that leptonic processes also make gamma rays. And so you can't uniquely say that something is a hadronic process if you only see gamma rays from it. So the other thing that we could use to have a handle on is neutrino production. So in addition to the neutral pions, charged pions can also be produced. Those will decay into neutrinos and leptons. And so we can say, okay, if we observe neutrinos, we can get a good handle on where the really high energy cosmic rays are coming from. And so this is really, the goal is to find neutrinos coming from an extragalactic source. And the telescope that we use to do that is IceCube. And so it is in Antarctica. It detects very, very high extragalactic neutrino events. They have tried to independently find sources, but the challenge, as you know, particle physicists will know, is if you're looking at the whole map of the sky and you're not using any priors, so you're not using any knowledge of sources, of known sources, then you get hit with lots of trials factors because there's a lot of places to look. And so when you just do a neutrino map independent of any other sources, it's really hard to say for sure if there's a source, a high statistically significant source versus not. And so this is what the IceCube collaboration published in 2017. They found a few hotspots. Those are circled in black. But really, this is an opportunity to use a knowledge, a prior.
I'm sorry, are all of these neutrinos in the map?
Yeah, so
Aren't
this
most
is...
of them atmospheric or something?
Oh, no. This is the high energy ones. So they do a cut to select ones that are not just atmospheric.
No, these are mostly atmospheric.
These are mostly atmospheric? Okay, I thought this was selected.
No, I mean there are 100 high energy astrophysical ones, but this is a map of hundreds of thousands.
Okay,
They're mostly atmospheric.
okay. Okay. Okay.
Well, I guess what's the energy cut, do you know?
Yeah, so I have to go back and look at the paper at what the energy cut was. I thought that the energy cut was TeV, but TeV is more probably not atmospheric.
No,
Yeah.
it's no.
T's-
Only
hundreds
above
of
100 TeV does the astrophysical fraction get to above 30%.
Okay.
Depends what declination in the sky.
Yeah. Okay.
This is the point source analysis.
Yeah.
So it's, as you say, about 1 TeV is the threshold, and it's mostly atmospheric.
Okay.
So these points are individual neutrinos.
Well,
So
these are
it's a likelihood.
clusters. There's a million, tens of millions of events in there, so you see hotspots.
You know, also the energy, so if it's very significant, like 6, the 10 to minus 6, then this is both. It's a very
But-
high energy one.
Yeah.
It comes where there's not a lot of
But sorry guys,
background.
I just want to understand what I'm looking at. All these points are in a catalog of IceCube as neutrino events, correct? These blue spots.
Those are so this is a likelihood map of where where neutrinos are coming from. So yes, they're not direct, it's not like a histogram of neutrinos, but it's a likelihood. And so this is the log, P is the likelihood, the log of the likelihood is the significance. And so you're looking at a significance map of where potential neutrinos are coming from. And so the darker the color, so you can see the likelihood is relatively low. It's like a log likelihood of 3 is not a super statistically significant detection.
Presumably they've taken into account the fact that the exposure is not completely uniform and therefore the atmospheric neutrinos will populate.
But their list is like millions of events.
Yeah, but what they're doing is they're trying to pull out the places there might be a
Excess,
non-atmospheric.
okay.
Yeah, so the higher energy ones are certainly weighted higher
Right.
than low. Maybe this is the best way to say it. The highest energy events, because they have a higher probability of being extragalactic, of being non-atmospheric neutrinos, those have a much higher weighting.
Okay,
Okay.
clear.
Yeah. Thank you. It's been a while since I thought about this map, so. And so there's lots of ideas as to what sources could accelerate protons, and one of them are active galaxies. And so active galactic nuclei are like a core of a galaxy that's actively accreting matter. They will be, so going towards the supermassive black hole, there's a region where gas and dust is actively being accreted, it is getting heated, and there's lots and lots of thermal emission. And it's a very dynamic environment that we are still trying to model and understand, but sometimes there will be flares that occur, especially if the jet of this is pointing at us, and we will see a rapid change in the light curve in gamma ray energies. And these are much, much higher energy gamma rays than for gamma ray bursts. And so these are in the hundreds of GeV area, whereas gamma ray bursts are in the hundreds of keV to MeV area. And so this is a variability map of the Fermi sky. So you can see this is things changing in its gamma ray intensity. And this is just as a function of time. So the gamma ray sky is very dynamic. It's not just static like in the picture that I showed. And IceCube started sending out alerts whenever they would observe high energy neutrinos starting in April 2016. And you could see these popping up in the map as we go along. And so they've sent out a handful of alerts. And crazily enough, also in 2017, that was like a really big fall because like August was the GRB thing, and then this happened in September. So like a month later, IceCube sent out an alert that they had detected a high energy neutrino, and it was coming from a particular well-known blazar.
Question.
Yes.
What's the resolution of IceCube?
What is the resolution of IceCube? It's tenths of degrees, maybe a degree, depending a little bit on the source class. So for this,
whether it's an electron neutrino or
a muon neutrino, exactly. Yeah. So, there. Okay. Yeah. So this particular neutrino was one of the ones that had higher angular resolution. It was a muon neutrino, and so it had relatively good position resolution, and not quite as good of energy resolution, but it entered through the side of IceCube. So what you're looking at, so IceCube is a detector that is made up of strings of digital optical modules that are embedded in the ice. As a neutrino interacts in the ice, it will interact with the ice and change into a muon, or it can do a muon, and then the Cherenkov light, because the particle is traveling faster than the speed of light in ice, it'll cause Cherenkov radiation to go through it. And so you get that radiation in all of these digital optical modules, the DOMs. And so it is a function of time. So the event came on the left. So those were earlier events, and then on the right, left. And the energy is proportional to the size of the blob. And so you could see where the energy was being deposited. And so where was this pointing to? So this is the night sky, if you're, again, looking at it with your eyes. In the Orion constellation, this blazar was sitting TXS 0506 plus 056, and this is what it looks like in gamma rays, and then you could see the transition of before the neutrino event occurred and then after the neutrino event occurred. So it increased. Something happened in the month or so preceding the neutrino event where this blazar went from being very steady state to being a factor of 6 higher in flux. And so we observed a change in that blazar. So something was happening. It was about 4 billion light years away. It was in the LAT catalog of one of the 50 brightest blazars. It isn't the brightest, but it is really like an interesting source.
What is the chance probability? Like, are we sure it was blazar created neutrino?
So, what is sure? I think it was about 4 sigma when you're looking at trials factors. It helps that like the neutrino is pointing to a specific blazar, but then you have to look at like the chance coincidence of there being any neutrino coming from any event at any time. And it was about a little over 4 sigma. The other thing that IceCube was able to do was look back in their historic data, and they found some lower energy neutrinos, about 13, coming from that direction as well. And so that helped increase the trials factor, but we didn't see a correlated gamma ray flare at the same time as those neutrinos were observed.
So it is not clear if this increases or decreases the likelihood.
Yeah.
Because the likelihood that the 4 sigma takes into account also the temporal window.
Yeah.
And if there is no correlation between the neutrino events and the gamma ray flare, then you have to take out this temporal coincidence or reduce its weight, and then it is not clear.
It's complicated.
It is
You
not
can't
clear
have
to
your
me
cake and eat it
that
too.
the extra 13 neutrinos are helping or are for or against the case.
By the way, Fotini, a fellow here, is one of the world's experts in this
Yeah.
particular phenomenon.
I'm slightly skeptical.
Yeah. I want to point out that they recalibrated the data recently,
Okay.
and the pointing changed. Now there's a 3 sigma discrepancy of the pointing of the neutrino and the TXS blazar.
Yeah.
But
Oh,
they have not-
discrepancy, so it is off.
You know,
It's off, yes,
No,
but,
no.
but they
it's
haven't recalculated the chance probability. of the-
borderline still inside the 3 sigma error circle.
Yeah, but it's the same. I mean, that's
Okay.
just
Yeah.
half full, half
Within
empty.
and the weight is the same.
What?
Yeah.
Okay.
I think it is fair to say that like, because I think that there's a lot of questions, because if we saw it from this particular blazar and this particular gamma ray flare,
Where are
there's
the
lots of
brothers?
things. I know there's other neutrinos that didn't come when a blazar was flaring. So like, I agree. There's a lot. It's a lot. But I would say, there's been a lot more things that I think are even more compelling that have come more recently, and I'm going to get to those. Yes.
So if indeed these neutrons are coming from the blazar, like is your working hypothesis some kind of merger process, or is something happening at the center? Or?
So that is the $1 million question, I think,
Alright.
is what is happening and where is this coming from? And actually, if you have, if you'd like to chat more about it, like it's hard. It's a little bit also challenging to explain the same physical process that would cause the gamma ray flare and the neutrino. Like it's.
I'm sure it's weak and man.
But when this happened, when we got the Ice Cube event, I mean, you know, I guess we had our muscles worked out already when we alerted everybody to follow up the GRB. So now everybody said, okay, everybody go look at this thing to see if we could get more data to try to follow it up. And so Ice Cube sent out the alert. Swift tiled over the region to get X-ray data for all there was something like 8 X-ray sources. So that's actually the Ice Cube neutrino error circle, the big oval one. And then all of those dots are pointings from the XRT. The XRT has a field of view that's on the order of a few arc minutes. And so that gives you an idea of Swift when it was tiling over. Of course, we looked through the LAT data. And at the time of the neutrino, so you can see the light curve of in gamma rays from the start of the LAT mission all the way to the time when the neutrino occurred. And so the flux increased by quite a significant amount during that time. So that's just, you know, a statement. MAGIC also followed up this blazar. And this was previously unseen for the Ayer-Cherenkov telescope, so this is even higher energies than the LAT, so this is several TeV. During this time period when the gamma ray flare was happening, MAGIC was able to observe this in very high energy gamma rays. So I think it's definitely not crazy that when it was flaring, you could see it at higher energies in gamma rays. The light curve, or the spectral energy distribution, shows going from radio all the way up to gamma rays that the radio and optical emissions, so that first hump, so for those of you who are used to looking at blazar spectral energy distributions, they're bimodal. The first hump is you know, particular kind of emission, and you see that was relatively unchanged in archival information when compared with the flaring state. So in all these other observatories we're looking at it.
The gray dots are the archival.
The gray dots are the archival, yes, thank you. And then when you actually see the transition is in the gamma rays and somewhere in the X-rays for that second hump. That's where the flux increased by a significant amount. And then if you plot, and so the LAT and the energies are all in the, you know, GeV. The very high energy is shown in red, and then the neutrinos are where they would be if you plotted them on the same spectral energy distribution. I will point out that there is a really big gap in the electromagnetic spectrum right now, and that's in the, you know, hundreds of keV to tens of MeV to 100 MeV. Right where the big blue X-ray word is there's no observations there, and it's just because we don't have telescopes there that observe in that area. And so I promised that there was lots of interesting stuff that have come out. It seems like there are some potential correlations between neutrino sources and tidal disruption events. So these are other black holes that are shredding apart stars actively and tidally disrupting them. One of, I think, the most interesting things that have come out of the IceCube collaboration recently is their observations of the Milky Way. So they were able to see the galactic plane in neutrinos, and that's shown, the top is optical, then the gamma ray, and then predicted based on the pion production maps, and then what you see in the neutrinos. And then there's a few additional active galaxies that are not blazars, so these are C4 galaxies, that I think are coming up as potential very interesting neutrino sources as well. And so NGC 1068 is one that's of particular interest. This isn't one that there's correlation with like a flaring gamma ray source or anything. It's a different thing. And then there's a few others that are in this classification that I think are also very interesting, and people are following up. And I think that's really where a lot of very exciting neutrino science is going to come. Yeah.
I wanted to comment on the tidal disruption event.
Yeah.
So there is this thing called IceCat2. It's the reanalysis of the arrival directions that Michael mentioned. So they're using machine learning to improve the angular resolution. And so there were 3 TDs correlated with 3 high-energy neutrinos, and
Right.
all of them are gone.
Ah, shucks.
Which
Yeah.
agrees with what we wrote when this paper was published.
Yes, it agrees with the stacking
That it
limits
is
as well.
impossible
Yeah.
that this neutrino was really correlated with the tidal disruption. I have a paper, this is written.
There was also other things. Like
Impossible
the stacking.
because of staking analysis?
Energies,
Or just energy?
energetics, just the simplest thing in the world, counting ergs. But it's, of course, it's much more exciting to say that this is correlated when you get a Nature paper which is cited by 500 people, but it was clear the moment it was written that it was wrong.
Nice audience you have.
I know. I mean, I think this is part of the fun about emerging fields, is there's a lot to debate. Yeah.
Just to
Sure. Yeah.
reduce the pressure. And the third image and the fourth,
Mhm.
one says neutrino predicted pi 0, and it's a very skinny signal. And then there's a new analysis expectation, and that looks really puffy.
Yeah.
Are they the same angular scale?
No. So what they did is, so this is like, if you're doing simulations, it's like the truth information, and then that's smeared through the detector. So
Oh,
like,
I see.
this is what you'd expect
If you had a perfect resolution, I see.
detector with perfect angular resolution. And then you see obviously a much broadening, because this is the event analysis uncertainty that they used. You see that big circle. And what was actually really interesting about this analysis was, in order to increase their statistics, they didn't just use the muon only track neutrinos to point back. They used the cascade events as well. And so it's a worse angular resolution, but your statistics go up by a significant amount. And so that's like how they were able to actually get a convincing signal out of that data, is because they had a sufficient amount of data to analyze. So it's a really, like I said, I think this is one of the coolest results that came out of IceCube.
And that held, that was actually when they did this refined analysis.
Yeah. Yeah, and so this is another piece to the multi-messenger puzzle, is trying to figure out where these neutrinos are coming from and what are these sources, and then ultimately understand where the hadronic acceleration is happening in the universe. And so this is where I'm going to shift gears a little bit, because I mentioned, I am more of an instrumentation person, and so one thing that I am thinking about all the time is, what do we do after Fermi? What do we do after Swift? Because both of these telescopes are, well past their prime observations. And, as I mentioned before, there's also gaps in our current observations and, the MEV gamma ray range. And a lot of these, we could learn a lot more interesting things about the universe if we could observe in this particular band. And so one of the things that I do is I'm developing silicon detectors, and these are very similar to the ones that are developed in particle physics experiments. And then, basically maturing them enough so that we could demonstrate that they would work on orbit. And so I'll start out by talking a little bit about silicon detectors. So the way that the LAT works is, for those of you who are familiar with particle physics experiments, this is very similar. So you have a silicon tracker, and the LAT converts the incoming gamma ray into an electron-positron pair. So the gamma ray interacts in the silicon material, electron-positron pair, you reconstruct that vertex, the vertex points back to where the source was. And so that's where our angular resolution comes from, is the accuracy with which we can reconstruct that vertex and point back to a point in the sky. Now, silicon has flown lots over, more than 20 years on orbit, and so it's a very well-established long history technology. However, that doesn't mean that there aren't really amazing improvements that are happening. And the next generation of silicon detectors is going to be CMOS detectors. And so everybody who has a cell phone camera has a CMOS detector in their pocket that they carry around. There's a lot of benefits to this technology. It's low power, it's easy to produce, it operates at room temperature, and we can actually integrate lots and lots of pixels to do better reconstruction of these kind of vertices, understand where the interactions happen within the silicon, which gives us better information about the incoming photon. So there's a lot of cool things that we could do with these kind of detectors. And so one of the projects that I work on is basically taking the state-of-the-art detectors that were developed in particle physics, optimizing them for use in space, and then space qualifying them. And so this is a student that I worked with, actually an undergrad student, who worked on characterizing detectors from Atlas. And so we, after this, set off a whole program called AstroPix to design, characterize, build, and test this silicon detector. And so this is our matrix. So this is just one detector of AstroPix that you can see mounted to a readout board. It's even an imaging detector, because we had a little copper sheet where AstroPix was etched into it, and we put it over the detector, put a radioactive source from it, and if you squint, you could kind of see AstroPix written there, so we can do imaging. Yeah, so far we've been having a lot of success. We're on our 5th iteration. It's currently being fabricated at the foundry right now. And then we'll continue building it into larger and larger and larger prototypes so that we could demonstrate that this will work on orbit. So prototypes. So I work at NASA, and one of the things that they really want to do is make sure that if you claim that something is going to work on orbit, that you've tested it really well. So there's a high probability of success when you actually launch the thing. And so we have an instrument concept, which many folks may be familiar with, AMIGO, which is the All-Sky Medium Energy Gamma-ray Observatory. And this is 4 different subsystems to detect and characterize gamma rays over 4 orders of magnitude. And part of that spot that we're targeting is the one that isn't covered by current telescopes, so that MEV range. It has a tracker similar to the LAT, which I just talked about with silicon. That's where we would put the AstroPix detectors, and then it has a low energy calorimeter and a high energy calorimeter and an anti-coincidence detector to reject gamma rays, or to reject cosmic rays. So we built a prototype that is a balloon-borne experiment that has basically miniature versions of each of the subsystems, and this is what it looks like on the bench. It was about, yay big, yay wide. And we took it down to Fort Sumner, New Mexico, to launch it. And so this was in 2023. So the upper right-hand corner, that was when we had integrated everything. Those are some students and a postdoc, and then the guy on the far left is a Los Alamos National Lab scientist that we work with. To give you a sense of the scale, the white frame is the gondola that we mounted to. Our detector was the silver box on top. That's a normal-sized human, so just for reference. And then on the bottom right, that was our team doing a compatibility test basically to make sure that we could integrate with the launch vehicle. Now the launch vehicle is a fancy way, it was just a big truck that had a crane where the balloon was laid out on. And the thing I just want to point out is, just for scale, remember, this is normal sized human, and then you'll see why I pointed that out on the next slide. So we launched from Fort Sumner, we're going towards Albuquerque. That is the balloon lifting off. It's not quite as dramatic as a rocket. But that's filled with helium. It gets to be the size of a football field when it's fully inflated. And that little thing that you see down there, that's the launch vehicle. And you can't quite see the gondola because it is so tiny relative to the balloon. The launch vehicle is just stabilizing the connection between the balloon and the gondola. And eventually you'll see it move a little bit, and then it will release, and you'll see the payload lifting off, and then you'll actually see it against the white background sky pretty soon. Let's see. Yeah, our students started an Instagram account and documented the whole ordeal of launching. And so, okay, it looks like that's, okay, the launch vehicle is moving, and they want to release it very gently. And let me tell you, when we were down there, I learned more about like atmospheric wind conditions in different parts of the column, because the wind had to be blowing very gently and in the same direction at all these different tables. It was really a cool experiment. And so that is the gondola. So that's human sized, and that's the balloon sized. Now, because obviously there's less atmosphere, this goes up to 120,000 feet. That's when the balloon fully inflates, is because there's less atmospheric pressure squeezing it down. The launch, or the flight lasted about 5.5 hours. We were at float for a little over 3 hours. The winds took us a little bit south and then a little bit towards the west, and we actually decided to terminate the flight at that point because it was about to go over like a canyon, and we were worried we wouldn't be able to recover our payload if we fell into a canyon. And so the way that it works is there's a little tiny ignition, it pops the balloon, and then you start to free fall. And then as you're free falling, parachutes open up, and then you parachute yourself down, but there's no way to control it. So you're really just hoping that you don't end up in a terrible situation. And 3 days after the flight was terminated, we were able to recover the vehicle. It did end up on its side and a little bit rained on, but for the most part we were able to recover everything, and we were able to turn the instrument back on, so everything was cool. The other thing that we're planning to do is to launch a sounding rocket payload, and so this is to take the Astropix chips independent of the rest of the subsystems, and we've integrated them into a sounding rocket payload. Now you'll see that's a normal human hand holding it for scale, and so this is quite a bit smaller, but sounding rockets are essentially missiles, and they don't go into orbit, they just have a parabolic launch trajectory. And so this also demonstrates a different kind of environment that detectors would survive. In particular, all the little fiddly bits of wiring, and we can measure cosmic ray rates on orbit using something like this. And so we're planning to launch this summer. And there's our, all the bits and pieces of it on the bench, and then it'll fit into a nice payload that's about a 20 centimeter cubic box. And those were actually just delivered last week, so that's pretty exciting. We have like the mechanical housing to build everything and put it together. So then I wanted to spend like, maybe a minute or so on, like, there's a lot of really exciting science that happens in gamma rays. I think there's a lot of really cool scientific discussions that we can have, and there's lots of really exciting science in addition to what I was talking about today, which focused a lot on the multi-messenger aspects. But right now we don't have a planned future gamma ray telescope in the works. And so if those of you, which I've been also saying all day today, if you're interested in, you know, the future of gamma ray astrophysics, it's imperative for all of us to really advocate for this kind of a telescope, to NASA headquarters, writing white papers demonstrating how important the science is. And there's a few ways that you can do this. The Physics of the Cosmos NASA Community Engagement Group has a gamma ray science interest group. They meet, I think, once a month or so, and they talk about the future of gamma ray astrophysics and how you could get involved. There's also a group, a science analysis group called SAG, and this is the Future Innovations in Gamma Rays. And they're writing up a report where they kind of are collecting the interesting science and will, you know, put it together as a white paper, potentially get some journal articles as well, maybe a journal edition dedicated to this kind of science. So if you're interested and you want to keep gamma ray science going, I would say advocate and get involved. And that's all I have. So thank you. Questions? Yeah.
What's especially interesting about 1 MeV? 100 keV, 1 GeV, we all have it. What do you expect to find at 1 MeV which we have not seen yet?
So that's a very interesting question. I think that one of the very interesting things that we could see in like the 1 MeV-ish range is these really high redshift blazars. Because we're seeing a higher prevalence of those in JWST data, so in the far infrared, or in the mid-infrared. And those will be really big blazars, very powerful blazars, and we think that they're redshifted sufficiently that the peak of their spectral energy distribution is going to be in the few MeVs as opposed to the GeVs, which is where the lat is. So that's one really interesting thing.
Like redshift 10, 20?
Yeah, well, like 20 is far, but yeah, like more like above 6, I think, is really what we're looking at. The 1 MeV is also where GRBs are that is like the higher energy part of their spectra. And so like if you're looking at a telescope that can observe from like 25-ish keV to like a GeV, you get a really good handle on their, you know, energy output from a single continuous instrument as opposed to piecing together several. And so I think there's a lot of interest in that aspect as well. There's also like a population of pulsars that peak in the MEV. It's a different population because we're talking about really 3 orders of magnitude in difference in energy.
Those are bad pulsars, difficult pulsars.
Bad pulse, yeah. I know. But you know, people like them. I don't know what to say about that. Yeah, so I don't know. Yes?
So is Amigo going to be like Fermilab? Will it just monitor the sky like uniformly, and also will it have polarimetry?
So yes, it's a wide field monitor similar to the LAT. Its observing strategy is similar to the LAT, and it will have some polarization capability. It's not going to be like an IXP kind of thing, but it will have, I think. Gosh, I don't remember how sensitive it was in the paper, but yeah, it'll have some sensitivity to polarization. Yes.
Well, first I want to apologize if I was too.
No, not at all. Not at all. People have opinions.
I come from a different culture, so I need excuse.
No.
And some people tell me that relative to others from my culture, I'm not so. Anyway, I want to return to this question about Andre's question about why. There were 2 historical.
Could you talk louder, please?
Sorry, there were 2 historical detectors in this range, COMPTEL and OSI, that were sent together with BATSI.
Yep.
If I remember the history correctly, they were supposed to be the highlight of the Compton GRO mission. And one could say that nothing came out of them, well, nothing that was really exciting.
Mm-hmm.
I think this is the basic reason. This gave a huge blow to this part of the spectrum. Now, it so happened that this is the third talk this week that I hear about the importance of 10 MeV or 1 MeV, but I'm also puzzled what is exactly that word, but you answered, but I just wanted to comment that there was already something there. And so as a question, I'll ask, is there any, how much more sensitive you expect to be compared to these dinosaurs? I mean, this was in the 90s.
Yeah. No, so I mean, this is I think every point you made is a very excellent point, right? Like, Comptel was supposed to be much more sensitive than it was. They ran into a lot of problems with their instrument background, which made, and I mean, actually so did Integral. Like, and that is what made them, I think, less scientifically capable than they could have been. I think Comptel observed something like 30 sources and a handful of GRBs, so like, it really was not a very sensitive telescope. It ended up that Egret and Batsy were the stars. They were the stars, yeah, they were the stars of Comptel, of CGRO. And
actually,
so
Batsy was not supposed to be on CGRO.
Oh, okay.
It was on CGRO because some other experiment went over budget.
Yeah.
And they throw it out and put Batsy in.
Oh,
Really?
that's funny.
Serious.
I didn't know that. I didn't know
Serious.
that.
This was not part of the 4 original experiments.
Oh, funny. Okay, well, it's funny the way that works because Batsy is a great instrument, right? And I think that we have a much better handling of the instrument backgrounds, which will, by default, increase the sensitivity by at least an order of magnitude. And based on the simulations that we've done, we can probably get 50 times without too difficult
Yeah, so we
of
have,
increasing sensitivity.
So you had a hunting license.
Yeah, so it's a lot. Yeah, it's a lot. It's a challenging region because you're working with Compton scattering, and COSY is a Compton scattering telescope that's going to launch next year, and it's in the 1 to 5 MeV. It's a small telescope, it's a small explorer, and so it's not incredibly sensitive, but it'll do a lot of like galactic nucleosynthesis. That's its main goal is to map out the galaxy and see where like the titanium lines and the iron lines and stuff are. So that's that, but they will really be a pathfinder to see if we have a better handle on understanding of instrument backgrounds and the backgrounds in the 1 to 5 MeV regime, which is what really killed Comptel.
And did you see anything in the trial that you did? Did you see, was there any astronomical observation in this trial? Because I'll tell you why I'm asking after you'll answer.
Yeah, so we really weren't expecting to see anything. It was only a 5-hour flight, and our detectors were about this big. So it was really just to demonstrate. So we did see photons. We reconstructed photons. They weren't from any particular source. They were just photons. What we'd like to do is build a bigger balloon payload that's actually, maybe like 50 by 50 centimeters squared, and then we could detect sources with that. If a GRB happened to go off, like COSY the balloon did detect a GRB from a balloon. We would certainly have sensitivity to detect the Crab or Vela or something like that in those energy ranges. And so that our goal is to have a follow-on flight in a year or two that would actually be able to do some science measurements, again, to verify that we could do what we claim we're doing.
Well, the reason that I was asking is another historical anecdote, because a Batsy prototype was flown on a balloon. And if they notice what they've seen, they would have actually scooped the discoveries of Batsy, because they saw a single GRB in the balloon flight, unlike quite a large number that they were expecting, and the single GRB was coming from the galactic pole.
Okay.
Which means that GRBs are not galactic.
Right.
And this could have been discovered in, I think, when was Bonchy launched? 90. This could have been discovered in the 80s.
Yeah.
With this, if they paid attention to what they saw.
Yeah.
Because they were expecting few,
Yeah.
about half a dozen or more, but in the galactic plane. And they saw one in the wrong direction.
Wow, yeah.
So,
Ignore it.
Look more
What?
carefully.
I know, we should look
I
at that
don't know
balloon
if it was
data
even
again.
published.
We should thank
Because
Regina.
they didn't pay
Sure,
attention
sure.
to what
Again?
they said.
Yeah, they did.
If people have questions, obviously, yeah,